talked about acids, and now we're going to talk about bases. Strong bases dissociate completely in solution, just like strong acids do. And so then the hydroxide ion concentration we can figure out directly from the concentration of the base. Most strong bases are metal hydroxides, group 1A or 2A. So sodium hydroxide is one that we use a lot, potassium hydroxide. These are also strong bases. Other metal hydroxides can be bases, but they're not very soluble. So what does dissolve separates completely. They're strong, but they can't be made very concentrated because their solubility is limited. So the group 1A metal hydroxides, very highly soluble, and so we can make concentrated solutions, and that's why we tend to use those. The group 2A, only slightly soluble, but they're going to produce 2 moles of hydroxide for every mole of base. So like strontium hydroxide, you're going to get 2 moles of hydroxide for 1 mole of base. So there may be a question on the next exam where it's trying to trick you with this, and it's going to ask you, like, what's the pH of a 1 molar strontium hydroxide solution? And you have to take into account there's twice as many moles of hydroxide as moles of strontium hydroxide. So watch out for that. We talked about diprotic acids. They have more than one ionizable hydrogen. Those hydrogens come off one at a time. Strong bases don't do that. They just dissociate completely. So these 2 hydroxides, they just both come off at the same time. Any questions? Strong bases are kind of boring. Weak bases, kind of like weak acids. Most of the common weak bases produce hydroxide by accepting a proton from water. So they don't actually have hydroxide in the formula. So like NH3, right? NH3 is a weak base, and you could look at that and be like, how do you make hydroxide? You have no hydroxide in you. It'll take a hydrogen ion from water to make ammonium ion, and that's what produces the hydroxide ion. So that's what weak bases do. Here, B just for generic base plus water. The base will get protonated, and then we have hydroxide ion. We had an acid ionization constant. We also have a base ionization constant. So here's the equation representing the ionization of a base. And so equilibrium constant is the products divided by the reactants. Water is here, but it's a liquid, so we don't include it. So BH plus times OH minus over B. And we call that KB, the base ionization constant. If KB is small, that means that it's a weaker base. The small equilibrium constant here means that it tends to stay on the reactant side. It's only going to ionize a little bit, and so it's not going to produce a lot of hydroxide. If you have a larger KB, that means these numbers are bigger and this one's smaller. The reaction goes more towards the products and produces more hydroxide. So that's a stronger base. And just like with hydrogen ion and acid ionization constant, we can talk about pKb. So pKb is just the negative log of Kb. Any questions? Here's some common bases, weak bases, given base ionization constants. Again, don't memorize those, please. I don't know, I don't remember them. So we've talked about ammonia. The 2 other ones that you've maybe seen before are carbonate ion and bicarbonate ion, also known as hydrogen carbonate ion. So carbonate ion can take a hydrogen from water to make hydrogen carbonate ion and hydroxide. So carbonate ion is a weak base. The hydrogen carbonate ion can also take a hydrogen from water to make carbonic acid and produce hydroxide ion. So those are going to be weak bases. The rest of these guys are, you can think of them as being relatives of ammonia. So ammonia is NH3. I keep jumping ahead of myself. I'm going to try not to do that today. And so we can think of the rest of these guys as just being substituted ammonias. So here this is NH2, and this was NH3. One of the hydrogens was replaced with a methyl group, but it's the nitrogen that's acting as the weak base. All of these guys, except for the carbonates, they have nitrogen in them. So if you see a formula and it's got nitrogen and just carbons and hydrogens, in Chem 1A that's a base, that's a weak base. Just is, okay? So here's ammonia. The nitrogen has the lone pair, and this is what allows it to act like a base, because it has to take a hydrogen ion from the water. And the hydrogen ion is not going to have any electrons. It's got nothing to hold on to the nitrogen with, so the nitrogen is going to use its lone pair to hold on to the hydrogen ion. And then that leaves hydroxide. This is methylamine, and here the nitrogen and these two hydrogens are the same, but over here, instead of a hydrogen, we've just got a carbon with 3 hydrogens on it. And that doesn't really do anything that we need to be concerned about in 1B. This is still going to act like a base, a weak base. Again, the lone pair on the nitrogen can take the hydrogen ion. Then this is protonated and it has a positive charge. And then this is left the hydroxide with a minus charge. Any questions about that? So these nitrogen-containing compounds are something you've not really seen before except for ammonia. Finding hydroxide ion concentrations and pH of basic solutions. As with the strong acids, when you have a strong base, the autoionization of water contributes hydronium ions, but it doesn't matter. It also contributes hydroxide ions, right? And it's just so small, we can just ignore it almost all the time. If we're trying to find information about a weak base, this is similar to finding information about a weak acid. We're going to ignore the contribution from the autoionization of water. We're going to make a nice table. We're going to use the Kb expression here instead of the Ka expression to find hydroxide ion instead of hydronium ion. Okay, it's very much the same. Any questions yet? Someday I'll remember the remote control. I actually know where it is at home. But can I remember to bring it with me? Okay, so this one, we're finding the pH and hydroxide ion concentration of a strong base. What if we didn't have that title? We're looking at find the hydroxide ion concentration pH of this solution. You have metal and hydroxide. That's a strong base. The other thing is you don't see them give you a Kb, right? So that's a clue that maybe we don't need Kb. So this is a strong base, and so we can write the equation for it ionizing, or this is dissociating. It's going to form a barium ion and 2 hydroxide ions. We get that from the chemical formula. So we've got 0.010 molar of the barium hydroxide we want to know what the hydroxide ion concentration is. So I'm just going to explain this to you in terms of stoichiometry, but you don't have to do it that way. Once you see how it works in your head, you're just like, oh, I just need to multiply by 2. So I've got 0.010 molar barium hydroxide. And I want to find out, actually, let's do this. Moles per liter. And I want moles per liter hydroxide. So I need to change this. Hello.
Hi.
Hi. This is my rambunctious class.
Well, fortunately, I don't recognize, I recognize one. I don't recognize anybody else, so that's okay. I'm the dean, so if you don't know me, that's good.
Yeah. Yeah.
Yeah. Hold that thought.
He didn't seem very upset about it. He's like, throw him in there too. How'd you do? How'd you do? What size?
No, did not.
Yay! I really like that.
No. Okay, I lost all my writing, didn't I? Let's see. So we have hydroxide, barium hydroxide, sorry. We want to know the concentration of just the hydroxide ion. So we want to know, we can use the mole ratio here. 1 mole of this makes 2 moles of that. So we're going to divide by moles of barium hydroxide because we want that to go away. Does this look kind of familiar? And then the numbers here come from the balanced chemical equation, 2 moles of hydroxide for every 1 mole of barium hydroxide. And we get 0.020 moles per liter hydroxide ions. So that's what's actually going on. But I think most of you are at a place where you can say, oh, well, there's twice as many hydroxides as there is this thing. So I'll just take my 0.01 and multiply it by 2. And that's okay as well. So that's the hydroxide ion concentration. It's one of the things we're supposed to find. And then they want the pH. Well, the pH is the negative log of the hydrogen ion concentration. We've got the hydroxide ion concentration. Remember the circle of pH? So we're on one side and we need to get all the way to the other side. So we're going to do 2 little calculations. So I like to go through pH plus POH equals 14 because the math is so much simpler. We could take this and 1 times 10 to the minus 14 and calculate the the hydrogen ion concentration. Or we could take this and find the POH and subtract it from 14, which just seems easier to me. So the POH comes directly from the hydroxide ion concentration, which we just found out. Negative. Lost my log button. There it is, right where it always was. So that's what my POH is. Quick review on sig figs. How many sig figs did we start out with? 2. And so in this POH, which is the log of that number, what do we keep? 2 decimal places. So that 9 is the last sig fig. I'm going to write down at least 2 more just to avoid rounding errors. Okay. Let's do this weak base solution. So here they're saying hydroxide ion concentration and pH of 0.33 molar methylamine solution, Kb equals this. And we might think, methylamine, I don't know what that is. Well, amine is like ammonia. This is a weak base. The biggest clue, though, other than the title, which you don't always have, is they give you a Kb. If they're giving you a Kb, this is a weak base. Do we need to know its formula? No, we don't. We can call it B, base. So we're going to need an ice table. And so we're going to, first we're going to choose a pen, because that works better. B, our base, plus water. It's a weak base, so it's an equilibrium. And so we're going to fill in the initial line. What's our concentration of the base? 0.33. We don't care about the water because it's a liquid. It doesn't show up in the equation. Initial concentration of BH plus, 0. And hydroxide ion? 0, essentially 0. So we put X in for the change. Over on this side, these are both 0, so these have to be plus X. There are times when they'll give you, you'll have concentrations up here, and this will be the minus X because the reaction goes in the reverse direction. But if you've got a 0, that has to be plus X. So this is plus X. This one's minus X. And like with the weak acids, we're always going to have coefficients of 1, which makes it nicer. So at equilibrium, this is 0.33 minus X. This is X, and that's X. Then we write the Kb expression. Well, I guess that's supposed to be a lowercase b. I got carried away. And so that's going to be, it's going to be.
He needs me for like 10 minutes.
Okay.
But yeah, I need to like tell him something
Okay.
about, there was something going on in the garage, so about that.
Mhm.
So can I like leave for 10 minutes?
Absolutely, absolutely. So we'll take the concentrations of the products and divide by the concentrations of the reactants. Do we put water in there? No, water's a liquid, right? Its concentration doesn't change. It's never going to show up in there. So we were told that Kb is this, 4.4, just 4.4, times 10 to the minus 4. I knew there was another 4 in there somewhere. And then we're going to put in our equilibrium expressions here. BH plus times OH minus is going to be X times X. I'm just going to write X squared. And that's going to be divided by 0.33 minus X. So same thing we were doing with weak acids, right? What are we gonna do next? Well, negative log of what, though? But we don't know the OH concentration yet. We have to figure out what X is. That's okay. That's okay. Yeah, that's coming up, but we're slow. So, no, don't be sorry. So we need to solve for X. We have two possibilities. We could use X is small, we could use the solver. The book's gonna use X is small. It's gonna work just fine. I just think it's easier to use the solver. So that's what I'm gonna do. 4.4 times 10 to the minus 4. And over on the right, we've got x squared divided by 0.33 minus x. X equals 0.01183. We're finding hydroxide ion concentration and pH. What does X represent? It represents the hydroxide ion concentration, right? Because we started at 0. So this, and they're always going to ask you about the pH, not the pOH. So then we have to do the extra step. So now here's our negative log. I'm going to use the unrounded number. So pOH, negative log of 0.01183, 1.9270. That's the pOH. pH is 14 minus that. $12.07298, 12.07. Any questions? So the book is going to report 12.08. Close enough. Uncertain digit anyway.